So we'll jump right into it because time is precious for all of us. Today we have Dr. Bobby Wilson from MIT. He's a postdoc there. I believe this is your first year, right?
Yeah, second semester.
Going on. All right, so Dr. Bobby Wilson and I have known each other for a while. We actually went to undergrad together. He graduated in 2010 from Morehouse. I graduated in 2009, so we have some classes together. We were on the Putnam team together, so we spent many nights hashing out math problems and things of that nature. So if you have any questions on how I was in undergrad for all of my students, he may be a good resource for you guys. He'll tell you how brilliant I was at that stage. So he'll be talking today on the interplay between fractals, projections, and differentiability. Because I know Dr. Wilson, I know he wouldn't mind, if you have any questions to just ask, because he talks about some fascinating stuff. So feel free to ask him a few questions. Of course, we'll open it up towards the end as well. But without any further delay, Dr. Bobby Wilson.
Thanks. Yeah, thanks for having me. Thank Sam for inviting me today. It's nice to be here. And yeah, I'll reiterate, if there are any questions, please, feel free to interrupt me. I actually prefer if it's done that way than not. It's good to have audience interaction. So yeah, so I'm going to talk about some kind of, geometric concepts that some of these things hopefully you guys are familiar with. And then we're going to talk about how we can use these different characteristics of sets in, let's say, the plane, okay, and show that they characterize each other in some sense, okay? So since fractals are really nice, I'll start off with just fractals. They're cool things, right? So here are some pictures of some fractals, okay? And I give the definition here. There are many, competing definitions of a fractal, but for us today, we're going to really talk about self-similar sets, okay? And if you're having trouble thinking or imagining sets in, 5-dimensional Euclidean space, then just think about sets in the plane, okay? 2-dimensional sets in the plane, okay? And so yeah, I have some examples here that are pretty famous. And what I want to talk about is, at least at the beginning, is for fractal sets, and the reason that they're kind of interesting is because of the dimension, I guess, or how we can define dimension of a fractal set, okay? So if I give you a line, okay, just a line, let's say an interval in an R2, and I say, what's a reasonable way to define the dimension of this line, right? Maybe you'll say it's one-dimensional, right? It's one line, it's one-dimensional, right? And if I give you a box in the plane, and it's reasonable to say that this box, this flat box, is 2-dimensional, right? And if I give you a cube in this space here, or this room, let's say, it's reasonable to say it's 3-dimensional, right? And you can keep going and going on, right? So what about numbers that are not integers, right? What about, can we define something that has dimension 1/2, or 3/2, or some number that's not rational, right? And fractals give very good examples of these types of sets. All right, so let's compute some dimensions, right? Before we compute some dimensions, actually, I want to show you my favorite fractal, okay? This is not it, but this is the first step, okay? We're going to define it iteratively, okay? So the first step is just a box, all right? Very normal and interesting. The second step, I take my box, and I look at the corners of my box, all right? And I take 4 copies of my original box, each of which is 1/3 of the length of my original box, right? And I put them in the corners, right? Simple enough. First step. We're not done yet, okay? Second step, I do the same thing to each one of those boxes, right? Each one of these corners is 1/3 of the size of the box that they belong to, okay? And so on, all right? And again, and I keep doing this into infinity, right? So typically, in the past, I would give this talk, I would give it on the board, I draw and things like this, and Sam's seen me try to do this before, and the drawings can get pretty bad. You can imagine me trying to draw this picture on the board, okay? Sometimes it would be a complete mess. I'm really happy that I have these pictures to show you guys today, right? It kind of illustrates it a lot more than what I can possibly draw, okay? and I would never try to draw something like this on the board. We'd be here all day. Okay. Okay. So this is my favorite fractal. It's called the four-corner Cantor set. Okay. So let's talk about dimension. All right. And so we're going to compute dimension based on the similarity scale and the number of copies, in some sense, at each step that we create. Okay. So, and I'll give it here. It's kind of a weird form. Okay. But we'll go back and we'll look at and actually compute some of these things. All right. And so I'll say the similarity dimension of a set in RD, R2 if you like. It's log K over log 1 over R. R is a similarity scale. From our previous example, the similarity scale was 1/3, and the K, number of new copies, was 4. Okay? So we go from 1 to 4 boxes, each of 1/3 the length. All right? So we say this is the dimension. All right? So let's compute some. Here's a Sierpinski's triangle. At each step, we take one triangle, and then we change it into 3 triangles, each of which is half the size or half the length of the original. All right, we'll keep doing this, right? So we can plug this in, get a nice dimension here, right? Log 2 over 3, strictly bigger than 1, which is kind of interesting, not 2, right? Here's a Koch curve or Koch curve, or however you pronounce Koch. Here, it's maybe not so easy to see how you compute the dimension, but what you would want to do and what you should do is look at basically one corner or one length of this triangle and go from there, right? So you take one length of this triangle and you get 4 pieces that make a crown, okay? So you're going from one length to 4 pieces, and the size is not completely correct here, but each of these pieces should be 1/3 of the length of the triangle, the side that it comes from, okay? And so again, we compute the similarity dimension, and we get log 4 over 3, or log 4 over log 3, again, strictly between 1 and 2, so non-integral, right? And then this is the nice construction we had before, and same dimension as actually the Koch curve, which is interesting. All right, so okay, so we have fractals, we have dimension, and yeah, I think more or less, I think maybe we have kind of an idea of what a fractal is and what dimension is. Right? So let's talk about rectifiability. So rectifiability, and I guess you can do this by etymological terms, right? To rectify is to make something straight or square, right? And we want to say certain sets or certain curves, let's say, are straight or square in some sense, okay? And the reason, the way that we typically do this is with just differentiable curves, right? You take a curve in a plane, or take a function, right, and take the graph of the function, right? A nice differentiable function. And you have something like this here. And how would you say this is rectifiable or differentiable or like a straight line in any sense? You would look at each point and you would draw a tangent line. Or in the sense you can find a tangent line to a point, we say that it's rectifiable or differentiable at that point, right? Okay, and so of course, what does it mean for this tangent line to exist? It means that when we blow up or we get really, really close to this point, eventually this curve looks like this flat line, right? Okay, so we want to make this kind of fuzzy. This is maybe too harsh for our types of sets that we like, right? We like fractals. They don't look like this, as we saw before, right? So we want something a little bit more fuzzy, right? So I'll get into kind of the heavier math now. First of all, let's define a concept that's maybe similar to what a curve is, but maybe gives us a little leeway. And I'll call that a linear set, okay? A linear set is something that has dimension 1, but maybe doesn't look, I guess it could look like a curve, but maybe doesn't look like a curve, okay? And in particular, what we want to imagine when we think about a linear set that's not a curve is a fractal set that happens to have dimension 1, all right? So I'll give this definition. This is a delta cover, and then I'll give the definition of a linear set. And I'll give the definition of this thing I'll call Hausdorff measure. And I'll sometimes call it Hausdorff measure, but an easier way to think of it is just length, okay? This is basically what I want to define, right? So this fancy H1 of E looks kind of complicated, but if we go back to our curve here, the measure here will just be the length of this curve. All right, so it coincides with length. Okay, so we have this concept of length, and we say that if E is a linear set or E has Hausdorff dimension 1, if we can measure this length in some reasonable fashion, meaning that we take the length or we do this process and we get a number instead of infinity or something like this. Okay. Okay, so now let's actually define what we mean by rectifiable. Again, it's a fuzzy way of defining differentiable, and we'll define it in this way. You take some set, and if you can, and I'll summarize what it says here in this definition, you take some set, and it's rectifiable if we can cover it by differentiable curves, okay? Maybe it takes infinitely many of these curves to cover it, but we can do it, okay? So this is what rectifiable means. And I gave like a kind of a very precise definition here, but more or less, I want my set E to be rectifiable if I can cover it by differentiable curves, okay? On the other hand, if a set is the opposite of rectifiable, and we call that purely unrectifiable, any curve, any differentiable curve I have for this set should not cover any part of this unrectifiable set at all, okay? And this is what I mean by purely unrectifiable. Take any differentiable curve, you take a set, and you want to say that it's purely rectifiable, take any rectifiable curve, it doesn't cover any of the length of the set E at all. All right, so just the opposite of rectifiable, opposite of differentiable. All right. Okay, so let's see, where do I want to go from here? Okay, so some examples. I said Lipschitz curves. A Lipschitz curves is basically differentiable, but not a continuously differentiable function. Okay. Piecewise differentiable curves, right? If you just take let's say a line, a linear function, and then you piecewise define another linear function, at that point where you define this, you have this kind of, I guess, discontinuity in the derivative, you typically wouldn't call that differentiable, but it is rectifiable, okay? Okay, what else? Oh, curves with finite length. This is not the most obvious thing, but any curve, continuous curve with finite length is actually rectifiable, okay? You can define a derivative almost everywhere for a curve with finite length, and therefore it is actually rectifiable, okay? Okay, and just countable unions of these types of sets. Any combinations you can you take some sets and you can just cover them, put a bunch of them on the plane, and that's rectifiable. In fact, if you take just segments in the plane with rational slopes, let's say, just take all of those, maybe of length 1, take the union of all of these lines, it looks like a star or something like this, right? This is rectifiable as well. Okay? Even though there's a lot of points where there's one point where they intersect all at one point, it's completely fine, okay? Okay. Projections. So we talked about fractals, we talked about rectifiability, and now we want to talk about projections, okay? And I start with just kind of the simple definition of a projection. All right, and this is just orthogonal projection, I guess I call it orthogonal projection, but of course you take a point x and a line, and you project, and this is the origin here, you project onto this point, the unique point that makes a right angle with this triangle, okay? And this is an orthogonal projection. But of course, I don't want to just limit myself or ourselves to just projections of points. I want to project whole sets of points, okay? And it's similarly defined, okay? And I give a really nice example here, which is curves. You take the curve and you project every point, and every point that you get from projecting each of these points, you combine them together, and that's your projection of the set. Okay? This is a new set, and it's called the projection of the original set. Okay? So you can see here my set E, and I don't know how good this red shows up on this, but my set E is this curve, and also this part of the curve as well. I project it down, and the red part, these two intervals, are the projection set, let's say. All right? Onto the line L. All right, so pretty straightforward. And so, again, let's actually do some examples. All right, this is a nice set and it projects onto some nice intervals, let's look at, again, the four-corner Cantor set and see what happens when we project. Right? So, and this is actually, you have to be a little careful here. This is a new Cantor set, okay? So I gave our first four-corner Cantor set, each new square was 1/3 of the length of the original, and this one I want it to be 1/4 of the length, okay? And why do I want it to be 1/4 of the length? This here, right? So the number of copies is 4, the similarity scale here is 1/3. If I change it to 1/4, then my dimension is 1, and we like one-dimensional sets. In fact, you have to be a little careful here. I defined rectifiability and pure rectifiability only for sets that are dimension 1, right? Because I assume that my length is finite. Right? So of course, if we want to continue with anything and project anything, we probably want to project one-dimensional sets. And the four-corner Cantor set with 1/4 similarity scale is exactly dimension 1. Okay? Okay, so I project this. I start off, I'm here. I project down, and the size of my projection is, I just compute the size of these two things. And I'm assuming that the original length of my square was just 1. Okay. After projecting down, I get these two red parts. Each of these intervals is size 1/4 because of my similarity scale. And so the size of this is 1/2. Okay. Okay, the next step, all right, I project again. I get 4 intervals of size, I think 1/16, all right? And then the size of this projection now is 1/4, okay? And as you can imagine, each step you get smaller and smaller geometrically, okay? And so again, I used to give this talk on a board. You can only imagine, okay? Okay, so 1/4 here, all right? And we can imagine through our iterations that the size of this projection gets smaller and smaller, okay? So let's recap. For a differentiable curve, this nice thing, you project down, you get a couple of nice intervals, and you're pretty nice. You're in pretty good shape, right? Your projection, the size of this projection is positive, right? For this, it looks like the size of this projection is getting arbitrarily small, okay? And so we know that some projections for fractal sets can be arbitrarily small, right? Which is kind of a weird thing. So I think I should note is that the size of this set in terms of H1, right, is not going to be 0. So it's not a situation where the size of the set is getting smaller and smaller, and so therefore, of course, the projection should get smaller and smaller. Okay, the size of the set at the end of this construction is length 1. Okay. Okay, so we're back to here. So I guess what I'm trying to get to is that we can make this, or we can make this this relationship that we kind of hinted at already. We can make this strong. Okay, we can actually say that there is actually a one-to-one correspondence in some sense between rectifiability, big projections, small projections, fractal sets, non-rectifiability. Okay. And so this is a theorem from 1927. It's pretty old. I mean, and it's really powerful too as well. And this is from Besekovich. And he proved, yes, if you're rectifiable, then most of your projections, if you take most of the lines, okay, almost all, actually all but one line, really, then the projection, the length of the projection will be positive, okay? And if you take something that's purely unrectifiable, then the length of the projection is arbitrarily small. It's 0 here, but what we really mean by a set that's not empty to have 0 length it means that its length in some sense is arbitrarily small. Okay. Okay, or it can be, I should say more precisely, it can be covered by sets which have arbitrarily small length, or segments that have arbitrarily small length. Okay. Okay, and so for almost every line, and what I mean by almost every, that's a little technical. We don't have to get into that now, but for almost every line, the projection is actually 0. Okay, and so what are the ideas here? And the first idea for why this is true is that a differentiable curve has a big projection like we saw before, okay? And we've shown that the four-corner scanner set has one projection at least that gets arbitrarily small, but it doesn't necessarily mean, and first of all, we didn't show that it was purely unrectifiable. Also, it doesn't mean that every purely unrectifiable set has to have small projection, right? But in fact, this theorem says that. And it says every purely unrectifiable set is dust-like in some sense, okay? And so what do I mean by this? You can forgive me if this analogy is a little weird. I've been working on it, all right? So let's see what you guys think. So let's say you take a clump of dirt, all right, and you hold it up to the sun, and it has a shadow, right? A dark shadow, just as dark as anything else, right? Right, and this shadow is in some sense a projection, right? Of course, that's kind of the analogy, right? That's why we care about projections, right? Okay, now you crush this clump of dirt up, and you throw it in the air, okay? Now you have dirt all over your face, but it's all in the air, or most of it, I guess, is in the air, right? And you look at the shadow that casts, right? It's still a shadow, and it's still there, but it's a very much fainter shadow, right? And this is basically what's happening, right? You're saying that a differentiable curve, a rectifiable set looks like a clump of clay, and the purely unrectifiable set looks like a set of dust, okay? And so its projection will be small or light, or its shadow will be really light, okay? Okay. So where I come in is, so we knew this theorem since 1927, and a couple years ago, I was wondering if this theorem holds in a more general setting, okay? Let's say we're not in RD. Let's say we're just in a vector space. However you want to define a vector space, just vector space, okay? We don't have orthogonal projections because we don't have this notion in a general vector space, okay? This is something that's really just for Euclidean space. All right, so we don't have a notion of orthogonal projection. We can kind of define some weird kind of notion of projection, but it's a little different. But does the theorem still hold in this situation? This is a question, right? So the first question is, does it hold in a d-dimensional vector space? Okay. And the second question is, okay, maybe it holds in a d-dimensional vector space, but what about an infinite dimensional vector space? So now we just leave reality completely, right? And then we say infinite dimensional vector space, all right? Does it hold still there? All right. So let's ask both of these questions here today. The answer to the first question is yes, okay? And this is not it's not a real theorem, this is more of an exercise, really. What you have to realize is that for any d-dimensional vector space, there exists a nice map between that vector space and RD, okay? And this map preserves differentiable curves in some sense, okay? It almost does, right? And so if you take something and you say that it's covered by Lipschitz curves in this d-dimensional space, then it's going to be, if you map it to RD, it's still going to be covered by differentiable curves. So more or less, these notions are the same, okay? They're fuzzy enough to be the same in both RD and just a d-dimensional vector space, all right? All right. So if you're thinking, so let me slow down and let me say that if you're wanting an example of a vector space that's not just the real, or just RD, or just Euclidean space, I guess what I would suggest is you think about RD, okay? But instead of having the norm where you take the squares of the sums of the component, you take the sum of the squares of the components, take the square root of it all, you just take the maximum component, okay? And then that's your norm in this vector space. It's not the same as RD. It has different kind of geometric properties. And if you do combinatorics, you can see this very clearly, that it has much different behavior in this space. Okay, but in our case, it's the same. Okay, and I'll note here I noted before. What do we call projections if we don't have orthogonal projections, right? And we'll do it in kind of a fuzzy way, hand wavy way. We'll say it's just a function, a linear function. All linear functions, okay, represent some projection, all right? And then a line is, of course, defining kind of a way that is meaningful on a d-dimensional vector space. Right? Okay. before I move on to infinite dimensions, I'll just provide some definitions. First is just a Banach space. I want to say Banach space because I want to say that that the vector spaces that we consider are nice. Okay, you can make vector spaces that don't I guess behave well. So I would like to at least say that we have a nice vector space. And then infinite dimensional Banach space is just one for which any finite set of points doesn't span the whole space. All right. All right. So the answer to question 2 is no. All right. And let me make sure I have no time. Okay. The answer to question 2 is no. Okay. And this is actually kind of strange. And so for me, when I first looked at this problem, I thought, sure. I mean, you can do this in some way. You can say you can give some weird way of defining things on infinite dimensional space, and everything is going to be fine. Okay. But in fact, it was not even close to that. And it's somehow in these infinite dimensional spaces, you can find sets that straddle the line between dust-like and clump-like. Okay. So this is the theorem we have, but I'll say it. So in infinite dimensions, you can find dust-like sets that have large shadows or dark shadows. Okay, that's the analogy in this case, right? And so the theorem we have here is that you take infinite dimensional Banach space, any one you want. There's a set that's purely rectifiable, not anywhere close to a differentiable set. It's got positive measure so that we're not just projecting something that's 0 onto 0. Okay, and the size of projection is big for every line. Okay, so this is the opposite of what happens in D dimensions. All right. Okay, so let me just give some kind of basic or small construction or some small insights on the construction of this set, and also mention that the other half of Besekovich's theorem, that rectifiable sets have big projections, that does hold, and that does still hold in infinite dimensional Banach spaces, but the other side doesn't. Okay, so I'll just define little L2. We take the set of sequences here, and in order to define distance and length and norm, we'll give these two, I guess, definitions that look more or less like RD Euclidean space types of length. Okay, and then the Hilbert space in this case is defined this way. But what I want to do is, okay, after defining all of these sequences, okay, here that have some structure, I want to actually do this construction. Okay, and someone actually before us provided a similar construction in little L2 only. Okay, and it doesn't give you everything, but it gives you something very close. All right, so I'll present that and give like a kind of overview of that construction. So this is the thing I said before, that this person DePaul, he constructed a set, again purely rectifiable, it has big projections, but for a significant set of lines in L2. Instead of saying mostly all of the lines have no or have zero projection or zero length projections, he found a significant amount of lines for which this happens. Okay, and I'll give the construction here. What we'll do is define just a set as the image of some function from an interval to our set of sequences. Okay. Choose a sequence that's in L2, but it's not in little L1. If you know what little L1 is, in other words, the sum of the sequences equal to infinity. Right? And so, and the example is just a, n equals 1 over n. All right, and so then you define these types of functions. Okay, these like kind of sawtooth things. Right, and it's for each j, for each index, you define these, and it's very simple. Right, it's nothing completely crazy here that's going on. I define these sets, and then I simply just let my function be the sum of these types of functions. And this more or less gives you everything you need. Okay? And so the reason I kind of wanted to kind of show this is because it's a very simple construction, right? It's a kind of very self-contained, it's very nice. You don't really need too many things. You can find it right here in your calculus class, right? And you just take a sum of these things, right? All right, so, I'm going to stop here after I've done all the constructions like that and just open it up for questions and stuff like that, all right? So thank you for listening.
All right, so if you guys have any questions for Dr. Wilson, feel free to ask away. Any questions? Yes, sir.
Oh, so, sir, you talked about, you talked about a map where you go from, like, RD space to your
D-dimensional.
two-dimensional space.
Yeah, yeah.
What would that map be? I'm thinking, like, that's somewhat similar from going to a Cartesian space going to a polar space, something like that. So what would that map be?
Yeah, so it's just a so what you do, and it's so the properties of this map is that it's by Lipschitz, and this is what preserves the differentiability of everything. But you just you map the ball in RD, let's say, into the ball in this d-dimensional space, and then of course you map it so that it's kind of tight. You don't want to map into a really small version of it, but you map it so that it's really tight to the ball in XD. And really the difference between these, the d-dimensional vector space and our Euclidean space is what the balls look like, right? So in Euclidean space, I tell you, give me the ball of length or of radius 1 at 0, right? You just know you can just draw a circle and then everything inside of that, right? But if you define it in some other general vector space, it'll be something that's symmetric in some sense, but radially symmetric, but it won't look like a ball in general. So you just map these two things together, and that's basically what you get.
So can I ask a follow-up question? So with the benefit of doing converting our RD space into the same other dimension, would it be more efficient calculation, like more efficient calculators? Is that the applicability of it, or?
So I guess the applicability is that sometimes you don't want, so you want to change what's important in your vector space. So if you're doing any applications and you want to define some vector space or something like that, and maybe the Euclidean norm doesn't really make sense for what you're doing your application, right? Maybe it's important that if you want to compare two vectors, that their ith component is bigger or less, right? And Euclidean space doesn't really do that component-wise, right? It just takes everything.
It allows to cover other dimensions that Euclidean space can't.
Right, exactly.
Gotcha.
All right, well, let's thank Dr. Wilson again for coming. If there are any more questions you can ask Dr. Wilson, we'll be around for the next 2 or 3 minutes or so. There are still some more pieces, so feel free to grab those. If you did not sign the form that went around, please see Dr. Vega in the back so that you can sign. Thank you guys for coming, and enjoy the rest of your weekend.
Oh, no problem.